plotting routines into the input. Okay, so now what we have is two images. We have the Darkfield image here and the Flatfield image here. So the Darkfield image, this again is the color axis is just expanded. This is from around 330 to maybe 400 counts for the Darkfield, and the Flatfield is from around 1550 to 2100 counts. If we take a look at a histogram, we can see the two different histograms between the Darkfield imaging and the Flatfield imaging. So anything between here and about here is useful signal, which can be used to actually generate that image data, and above that is, you're not going to get any counts above that. That's just a limitation on the power on the X-ray tube. This is a very low power X-ray tube. It only goes up to 35 kV and 0.1 milliamps. So it's very, very low power. You need, to get this to around 65,000, you'd need around 32 times the photon flux to saturate the detector. So it's well below the maximum exposure that the detector panel can handle, but it still has sufficient power to generate images with very low noise after correction from the Flatfield and Darkfield. So the Darkfield image you've seen before, that's just variation in dark current on the CCD. The Flatfield image, on the other hand, you can see variations in sensitivity over the spatial area of the detector. This fall off here is likely not due to heel effect, since this is on the up-down axis. Any heel effect would actually show up on the left-right axis, because the anode cut, the angle of the anode cut would be on the left-right, so you would start seeing, if there was any heel effect, you'd start seeing it towards the edge of the image, not towards the top. So this is likely due to variations in sensitivity of how much of the cesium iodide scintillator on the detector surface. Now, one of the things that I do want to show you is that if we open the color bar editor and zoom in really far on the color axis, just go from 1850 to 1940, 1950 perhaps. Okay, and then we're going to zoom in on the Flatfield image. Just maybe a little too far in. Alright, so what you can see here is a hash-like pattern on the image. And this is actually the X-ray absorption of that carbon fiber plate, that carbon fiber sheet that's used to protect the image sensor. And by performing that Flatfield Darkfield correction, you can remove both that Darkfield dark current and the Flatfield inhomogeneity in the X-ray sensitivity. You just remove that mathematically. You can also see that Darkfield variation showing up in the Flatfield image. So to perform that Flatfield Darkfield correction, what you do is you take an image of an actual object. You would subtract the Darkfield, which removes any dark current, and then you divide that by the Flatfield minus the Darkfield. So that would compensate for that inhomogeneity in any X-ray beam effects and in effects of the sensitivity of the detector and the carbon fiber plate. So that would give you a much clearer image. So that will substantially reduce the noise in the X-ray system.